Welcome to Power Electronics Education Electronic Book, Lecture 4, Control Rectifiers. This lecture is presented by Dr. FIRUZ ZARE. Now let's consider a single-phase full-wave rectifier based on an inductive load. That means here instead of resistor we have an inductor. So again, when the input voltage is getting positive, then we can turn on this thyristor and this thyristor. So applying the gate signal at this time or this firing angle into thyristor T1 and T4, we can turn them on. In this case, input voltage appears across the inductor. Suppose that the current through the inductor is continuous. That means this is the current through the inductor. So at zero crossing, because the current through the inductor is positive, so that's why this thyristor and this thyristor still are on. So we cannot turn them off when the input voltage even is negative. So in this case, the output voltage is this area plus this area. So now in the second half a cycle, just at this firing angle or this time, we turn on T3 and T2. So what's happened? Because the input voltage is negative, so T1 and T4, they conducted because of load current, which is continuous and positive. But once we apply gate signal into these thyristors, then we turn off this thyristor and this thyristor. Why? The reason is that we provide negative voltage across these thyristors. For example, when the input voltage is negative over this cycle, when we apply gate signal at this firing angle, we turn on this thyristor and turn on this thyristor. So what's happened? If you look at this polarity, so we have positive here, and because this terminal is negative based on this polarity, that means the cathode is positive with respect to anode. We turn off this thyristor. And if you look at this thyristor, when we turn on T2, again this polarity is positive. That means this polarity is negative because this thyristor is on. And based on this positive voltage, you can see that this thyristor should be off because cathode is positive with respect to anode. That means the voltage across the thyristor 4 is negative, and the voltage across the thyristor 1 is negative. So in this case, this thyristor should be turned off. So this is the output voltage again when we turn on T1 and T4, and this is the output voltage when we turn on T2 and T3 or T2 and T3. Now we can look at the input current. Basically, input current is not sine wave because output current is continuous, and when T1 and T4 they conduct, this is the direction of current, which is basically positive. So that's why this is the direction of current. This is the direction of current. That means negative. So that's why we have AC input current, which is not sine wave. And in high power applications, if the load current is significant, very large, that means we inject significant current into the system, power system, and that's why we need to control the current. We need to control the harmonic. Now let's find the output voltage for a single phase full wave rectifier with an inductive load. suppose that input voltage is sine wave, because when we turn on the thyristor, input voltage appears across the output. So we can define output voltage for this period. That means starting from T1 till this point is T over 2. And because we turn on the other sets of thyristors, so this time is T over 2 plus T1. So based on this simple equation, we can find the average voltage over this period, which is basically finding this area. That means the lower limit of integral is T1, which is basically this time, and the upper limit of the integral is T over 2 plus T1, which defines this time. So we can solve the equation and find this answer, because as I mentioned before, if we have sinus AT, so the integral, when we have the variable of integral as dt, so this one means minus 1 over a cosinus AT. So this is basically, this term is 1 over a, and this factor is a. So this is the lower limit of the integral, and this is the upper limit of the integral. So then we can put the limits of integral in this equation. So from the upper limit, we can basically simplify, because minus cosinus 2 pi over t times of upper limit, which is basically t over 2 plus t1, and if we multiply, we can get minus cosinus pi plus 2 pi t times of t1 is 2 pi t1 over t. So that's why we have this term. And if we put the lower limit in this equation, we can get cosine 2 pi t1 over t. So we can define this equation in terms of firing angle, because if this is the firing angle, so that means this point in time domain is t1. So because one cycle can be defined as 2 pi, so then we can say that alpha in this frame equals to t1 in time frame. Then we can find t1 in terms of alpha and t. So when we put t1 in this equation, we can simplify, because minus cosinus pi plus 2 pi t1 over t equals to plus cosinus 2 pi t1 over t. So that's why plus cosine 2 pi t1 over t plus cosine 2 pi t1 over t means 2 times of cosine 2 pi t1 over t. And then we can simplify this equation, and instead of t1, we can put this equation, which means cosine alpha. That means we can find the DC voltage for a single phase half wave rectifier with an inductive load in terms of firing angle. This is a 3-phase half wave rectifier with a resistive load. basically we have three phases, VA, VB, and VC, which are described here, shown here, VA, VB, and VC. In this case, we define the firing angle with respect to this point. That means when we have positive voltage across any thyristor, then we can apply a gate signal into the gate terminal to be able to turn on the thyristor. So let's start with phase A. So beyond this time, phase A is greater than other phases. That means the voltage across this thyristor is positive. So when we apply gate signal, we can turn on this thyristor. So that's why when we apply gate signal just at this time, because the voltage across the first thyristor is positive, so we turn on this thyristor. So in this case, the voltage across the resistor is VA over this cycle. So the point is that the thyristor is in on state until this time. So at this time, we apply gate signal to the second thyristor, which correspond to the other current loop. In this scenario, when we apply gate signal, basically the phase B is greater than phase A, but because this thyristor conducts, so that's why the voltage across the resistor is still phase A. But at this time, because we apply gate signal to this thyristor, the second one, that means the voltage across the first thyristor becomes negative, so that's why we turn it off. So if you look at this current loop, in this case, over this period, T2 conducts, that means T2 is on, and because phase B, as you can see here, is greater than other phases, so the output voltage equals to phase B. Suppose that the voltage across the thyristor is 0. Then it's the same scenario for the next cycle. That means the output voltage is basically phase B and is decreasing just at this point. If we apply another gate signal to third thyristor, then we can turn it on. And because phase C is greater than phase B, so that's why the voltage across the thyristor will be negative. So that's why over this cycle, T2 is getting off and T3 will be on. So this is the other current loop for the time that we apply gate signal over this cycle. We can also look at the voltage across one of the thyristors, for example, the voltage across this thyristor. So basically, when we turn on T1, suppose that the voltage drop across the thyristor is 0. So that's why over this cycle, the voltage across the first thyristor is 0. And here, because T2 conducts, so what's happened, the voltage across this thyristor is VA, and here we have VB. So that's why the voltage across this thyristor is line voltage. And here, because the voltage across this thyristor is VA minus VC, so over this cycle, the voltage across thyristor is VAC. So that means when the thyristor is off, line voltage appears across the thyristor. So in order to find the output voltage in a simple way, we need to move the time frame. That means we just move the axis from this point to this new point. That means 0 is here, and we can define the upper limit and lower limit. So basically this period is t over 3, and suppose that we define the firing time as delta t. So in this case we can define output voltage as a cosine wave, because this is a sine wave, this is a sine wave, Vm sinus 2 pi t over t with respect to this point, this zero crossing point. Because we move the time axis to this new time, so in this case we can define this one as a cosine. So that means the output voltage is defined as Vm cosine 2 pi t over t. Now we need to define the limits of integral. So basically, because this time is t over 6, and the reason is that whole period is t over 3, so the half of that one is t over 6, and because the firing angle or firing time is defined as delta t, so this point is t over 6 plus delta t, and this time is minus t over 6 plus delta t, and the reason is that this time is minus t over 6. So in order to find the output voltage, we need to find this area, which is basically can be defined as this integral, where the lower limit of integral is minus t over 6 plus delta, and the upper limit of integral is t over 6 plus delta t, and over one cycle, which in this case this cycle is t over 3. So then we can find the answer cosine if this is alpha, or if this is another variable like a. So integral of cosine a t dt is 1 over a sinus at. So that's why cosine at is sine at, which is basically this is a, and this factor is 1 over a, and these are the lower and upper limits of the integral. So when we put the limits of integral, we can get these two terms. That means instead of t, we can put the upper limits of integral, so we get this equation, and instead of lower limit in this equation, we get this term. So now we can basically simplify this equation, because if we define the whole term as a and this one as b, so in this case we have sinus a minus sinus b, which is equal to 2 sinus a minus b over 2 times of cosinus a plus b over 2. So if we subtract a from b, we get this equation, and if we add a and b, we get this equation. So we can simplify them into the following equations. That means this term is sinus 2 pi over t times of t over 6, which is basically equals to sinus pi over 3. So this term, and we have this term as well. So we can also define this equation in terms of firing angle alpha. That means if one cycle is 2 pi, so delta t in this case can be defined as alpha, and because this is defined as delta t, which can be defined as alpha. So when we put delta t in this equation, and because sinus pi over 3 is root of 3 over 2, so we have this equation. That means this term, which is equal to 3 Vm over pi times of root of 3 over 2, which is basically this term, and cosine 2 pi delta t over t, when we put alpha in this equation, is cosine alpha. So the output voltage for a 3-phase half-wave rectifier is given this equation. So we know that in a control rectifier we can control the output voltage by changing the firing angle. So in this case the firing angle is changed to 45 degree, so that means 2 pi equals to 360 degree. So 45 can be found in radian based on this equation. So when we increase the firing angle because of resistive load, the point is that basically from this point the output voltage is phase A. So let's concentrate on this period. So let's look at phase A. When we apply gauge signal at this time, we turn on T1. So the output voltage is basically equals to phase A. So phase A is decreasing, and finally at this zero crossing, the phase A is getting negative. If we have negative voltage across the resistor, that means the output current should be negative. That means the current through this thyristor should be negative. But in this case, thyristor is turned off. So that's why when we increase the firing angle, because we may have negative voltage across the resistor, so in this case we turn off the thyristor. So we can actually split this period into this interval, which means T1 is on, and over this time, which means T1 is off. So this is natural commutation. That means we haven't forced this thyristor to be turned off. This thyristor has been turned off because of this type of load, because of resistive load. That means because the output current is getting negative, so that's why this thyristor is getting off. So when we change the firing angle, then we can see that because of resistive load, so thyristor is turned off at this zero crossing. So in order to find the output voltage, we need to basically find this area. That means the new limits of integral is this point, and in this case we can basically find the output voltage with the mu equation. We can find the output voltage for a resistive load when we have different firing angle in which that the thyristor is getting off for short time. That means the output voltage is not continuous. So in this case we need to define this limits of integral and find the equation. So similar to the previous description, we can find the output voltage based on this integral. The only difference is that this limit should be defined, which is basically t over 4. And the point is that when we actually define this time frame, so a quarter of cycle is t over 4. So that's why the upper limits of integral is defined as t over 4. So we need to find and simplify this equation. So when we put the upper limit and the lower limit in this equation and solve this one, we can get this equation. That means putting the upper limit in this equation gives sinus pi over 2, and lower limits in this equation gives sinus 2 pi over t minus this term. So when we simplify, because sinus pi over 2 is 1, so this is the equation. So we can simplify this equation. So we get minus pi over 3, and then we get 2 pi delta t over t. So finally we can simplify this equation. That means again we can find delta t in terms of alpha. In this equation is alpha t over 2 pi. So when we put in this equation, we can find the output voltage in terms of firing angle for a resistive load when the output voltage is not continuous. So let's compare a three-phase half-wave rectifier with an inductive load when the firing angle is 15 or even more with a resistive load. So in this case, when we have an inductive load, suppose that the output current is continuous. So what's happened at this firing angle, starting from this point, because phase A is greater than other phases, that means the voltage across this thyristor is positive. So once we apply gate signal, we can turn on this thyristor. So once we turn on this thyristor, this point, which is phase A, is connected to this point through this thyristor. So output voltage equals to phase A. Suppose that the voltage across the thyristor is 0. So that's why over this time, this period, so the output voltage equals to phase A. And because we have inductive load, so we have almost input voltage or phase A across the load. So in this case, because phase A is not getting negative, so this scenario is almost same as resistive load, but at different firing angle we may have different voltage waveforms.